Hi all. We're going to continue the discussion on the solution of second-order ODEs near a regular singular point. And in particular, today we're going to discuss applications to what is called the Bessel equation. That is very fundamental to many applications in engineering and the sciences as well. So what is the Bessel equation? We have seen this in earlier lectures. It's a second-order equation, looks like that, with one parameter, nu square here, that defines the order of the differential equation. You can see that x equal to 0 is a regular singular point, and I'm going to show you this again as a reminder on the next slide. And we're going to consider three cases of nu equal to 0, nu equal to 1/2, and nu equal to 1. And nu equal to 0 is a Bessel equation of order 0, nu equal 1/2 of order 1/2, and nu equal 1 of order 1. Now we're going to take these particular cases because you will see that the type of solutions that this Bessel equation gives you are fundamentally very different. And as a matter of fact, we're going to see all the different cases we discussed on the last lecture regarding the nature of the roots of the indicial equation appearing in this application to Bessel equations of different order. Before we proceed, let me just say that this is maybe the first time in your mathematics courses that somehow you will learn about solutions to, you will learn about functions like the Bessel functions, that they are known from the differential equation they solve rather than the way they look, because the way they look is rather complicated to remember. The differential equation, on the other hand, what you see on the top is very well known. All right, so let me remind you that x equal to 0 is a regular singular point. And so what we're going to do is we're going to compute these limits that you see in these equations on the middle. Because q and p are polynomials, we can see that x equal to 0 is a regular singular point because these limits that you see here are finite. I remind you that in the most general case that we had used, and we will use also today, these expressions that you see here, like x minus x0 times capital Q over capital P, these expressions being analytic functions at x0, is a generalization of what we see with the equations that I have here. So anyways, x equal 0 is a regular singular point because these limits exist and they're finite. So you can actually see q over p is x over x squared times x. So I'm taking x0 equal to 0. So x squared over x squared equal to 1. And this limit here is minus nu squared. So this, they define the indicial equation as we have seen on the last lecture. So if you plug in p0 equal to 1 and q0 equal to minus nu squared, you get this quadratic equation, and immediately you can see that it has roots that they are plus minus nu. I remind you p0 and q0, they are the leading terms in the power series expansion of these expressions around x0, all right? And this is what is coming in the indicial equation that relates the general differential equation with the corresponding Euler equation. All right, so what we are going to do is we're going to consider for x greater than 0 the three different cases of order of nu equal to 0, of nu equal to 1/2, and nu equal to 1. So let's take the Bessel equation for the 0 with nu equal to 0. Okay, so we are going to assume solutions in a power form. Okay, that are an x to r plus n with a leading coefficient not equal to 0. And if you take derivatives of this, we have done this multiple times in the last lecture, so you can differentiate term by term to get y prime and y double prime, and you can substitute everything to your differential equation, and you obtain this nice equation that you see on the bottom of the slide. Notice that in this equation, we do not have to take any power series expansion for the coefficients, because all the coefficients were already in a polynomial form, so we do not have that complexity for this Bessel equation. All right, so we have something that looks like this. So what we need to do is we need to write it in a form that will allow us to derive equations for all the coefficients an in a recursive manner. So so notice that here I have x to r plus n, x r plus n, and here I have x to r plus n plus 2. And I remind you this x r plus n plus 2 came because there is x squared here. X squared times y will give you x to r plus n plus 2. So somehow we need to change the indices here so that we get something that looks x to r plus n. All right, so let's see how, if we can do this. Can you actually see on how this is possible? So let me see what I have done here in going from the equation on the top to the equation to on the middle. So if you take the n equals 0 term from the first series, you're going to have a0 times r minus 1, which looks to me like this term. If you take the n equals 0 term from here, you will get an a0 times r, right, for n equal to 0, which is that. So this multiplies x to the power r. And then we're going to have an a1 r plus 1 times r, which is this. And then an a1 times r plus 1 coming from the second power series expansion multiplies x r plus 1. And notice this thing starts with n equal to 0, it starts with x to a power r plus 2. So effectively what I can do is I can take all the terms from n equal to 2 from here and all the terms with n equal to 2 from there, which is this, and combine it with all the terms from this series, where now you notice I have switched indices, writing this series as a summation from 2 to infinity of a n minus 2x r plus n. Can you see this? I mean, if you take the first term of this, will be x0 times, x to the power r plus 2, and you can see from here, for n equal to 0, you get a0 x to r plus 2, and similarly a1 to x r plus 3, and again here you can see for n equal 3 you get a1 to x r plus 3. So basically we're shifting indices by 2 in this last summation to get this. So we have written explicitly xr plus 1, and then the remaining terms xr plus 2, xr plus 3 with this summation. Okay, so now we can simplify a little bit the brackets here. We have r squared minus r plus r, so you have an r squared. You have something like this. And I remind you, this is again for the 0th order Bessel function. So the initial equation for this particular case is given by this term here. It's r equal to 0. So we have two solutions that they're equal, and they're equal to 0. Okay, so we will immediately, we know when we have two solutions that they are equal, we have to be careful on how we define y2 to be independent from y1. Okay, so So notice that if r is equal to 0, and this whole coefficient here needs to be 0, a1 has to be 0. All right, can you see this? This whole thing has to be 0, but we set r equal to 0, so the only way for this to be the case is for a1 equal to 0. And then you notice from this bracket to be 0, the coefficient of x to a power r plus n to be 0. We need to have this is the case. So if a1 equal to 0, notice that a3 will be minus a1 divided by this term, so a3 will be 0. And then a5 will be 0. So all the odd terms will be 0 when r equal to 0. So we can actually concentrate only on the even terms and write this recurrence relation the way that you see here. Okay, so I want to emphasize that as we did in the previous lecture, that when we write these coefficients, it's a good habit inside parentheses to indicate for what value of r these coefficients are computed. And in our particular case, we're computing this for r equal to 0. Remember, r equal to 0 is our double solution of the indicial equation. So this recurrence equation can be applied to get us the coefficient a2, and then a4 in terms of a2. And if you plug in a2 from here, you can get a4 in terms of a0 and a6 in terms of a0. And eventually, you get this wonderful formula that gives you a of 2m in terms of a0. And immediately, you know what the solution y1 is going to look like. Remember here on the front, we're supposed to have x to the power r, but r is equal to 0, so x to the power 0 gives me 1. So I get a very nice solution in this simple form. And you notice, of course, that this solution converges for all x's. And usually what you see inside this bracket or the summation itself is affiliated with what we call the Bessel function of the first kind of order 0. So let me give you this with some notation. So this is the Bessel function of the first kind of order 0, 1 plus this summation. And if you want to see this function with a plot, it looks like this darker line on this plot. At x equal to 0 starts with 1. And you notice it looks, it is oscillatory, and I'm going to come back to the nature of this. The different little curves that you see are approximations for using different number of terms in the expansion. So if you use 20 terms, you capture the solution correctly up to this point, but then you need more and more terms if you want to capture the solution correctly for higher and higher x value. All right, so we learned one of our Bessel functions, this J0 of x. So it's a Bessel function of the first kind of order 0. Order 0 refers to the fact that nu equal to 0. So what we need to do is we need to find now another solution that is independent of J0 or independent of equivalently of y1 to complete the solution for the order 0 Bessel's equation. All right, so if you remember, when we have two solutions that they are equal of the indicial equation, we can actually compute in series expansion the second solution, and that involves evaluating the derivatives with respect to r of the coefficients an of r, and then once we differentiate, we take the values of these coefficients evaluated at r equal to 0, which is our double root. So if you look carefully at the equations that we have, if you remember, we said a1 equal to 0, all right? So the derivative of A1 then it's equal to 0. And similarly, we had a recurrence equation that looks like the one that you see here. And you can see that for all the odd terms, because A1 of 0 is equal to 0, if you take this equation and you apply it iteratively, recursively, you will see that the derivatives of all the odd coefficients are equal to 0. So we have to concentrate only on the derivatives of the for even ends, right, to compute the coefficients for y2 for this case of equal roots of the initial equation. Again, the only thing that the slide shows is that in evaluating these derivatives, we only have to concentrate for these even terms, because the derivatives for the odd terms are 0, and those derivatives are 0 because A1 is 0, and as a result, A1 prime equal to 0, and then all the derivatives of all the odd terms will come to be equal to 0. All right, so this is the expression that we have for A to M, for M greater or equal to 1. And I am not going to do the derivatives here, but actually it's a simple 1-2 line type of calculation. If you differentiate this coefficient with respect to R, you will get this wonderful equation that the derivative of A to M divided by A to M is given by this expression that you see on the right-hand side. And if you now evaluate this at R equal to 0, you get this nice expression. And so effectively, I can summarize the derivative as minus a coefficient HM, which is given by the expression that you see here, times this term. Again, I have done nothing but you remember that evaluating the derivative from here is this expression that I'm going to call it H times the coefficients, and we have the coefficients given in, if you evaluate this at R equal to 0, we have an expression for those. So effectively, we have an expression for the derivatives. And if you take A0 to be 1, this is the general form of the solution for the second fundamental solution of the ODE, Y2, that is independent of Y1. I remind you, in the case of equal roots, right, we had these coefficients that they are the derivatives of the A's that we discussed in the previous slide. And then there was a leading term, which is the Y1 solution, which here we take it to be the Bessel function of order 0. Okay, this is the J0 solution, but with a singularity defined by log of x. We discussed this for the case of equal solutions in the previous lecture. So the only thing that is new here is computing these coefficients by doing differentiation of our recursive formula for the coefficients an. Okay, so we basically have y1 and y2. Now let me just say that you can actually take this to be a Bessel function of order 0, but in reality, what we do is we define a combination of J0 and Y2 to be a Bessel function of the second kind of order 0. So this combination involves this constant that you see gamma here. And this constant introduced by Euler has a very specific value and meaning that it's really of no interest to this class, but I want you to simply look at this expression, and there is nothing but a combination of the Bessel function of the the first kind of zero order that we computed, plus the solution y2 that we evaluated 1 or 2 slides ago. Just a linear combination, and the linear combination involves this coefficient gamma that is known as the Euler-Mascheroni constant. That's approximately 0.5772. And so this is our new Bessel function. It's known as the Bessel function of second kind of order 0. Okay, so if you explicitly plug in y2 in this expression for y0, then you can actually get this Bessel function of the second kind of order 0 to take the final form that you see on this slide. And again, I mentioned that these functions are remembered with the equation they solve rather than the expression they have. Sorry, there's little chance that you will remember this expression tomorrow, but there is a high chance that you will remember the differential equation that this particular function solves. Okay, so the general solution of the Bessel's equation of order 0 is obviously a linear combination of J0 and Y0. I am summarizing the two solutions, the two Bessel functions of the first and the second kind. Again here, notice that these solutions for J0 goes to 1 as x goes to 0. And notice that y0 has a logarithmic singularity here, right, at x equal to 0. Okay, so one of them behaves very well with no singularities. The other one has a logarithmic singularity when it comes to J0 of x. Okay. Now, if you do need a solution to this Bessel equation of order 0 that is bounded, then you will actually use J0 and you will not use Y0. If I can give you a plot, you can see again the J0 solution and the Y0 solution. You can see the J0 solution starts from 1, Y0 at x equals 0 blows up. Okay. Now, you may notice by looking at this picture, these functions, they look very much like sine and cosine functions. The only difference that sine and cosine basically have constant amplitudes. And as you can see, these two functions have amplitudes that decay, but there is a similarity with the sines and cosines. And this is not very surprising, because if you look at the differential equation and you take the values of x to be very large, then the second term is negligible, and this minus nu square over x squared is negligible, and the differential equation becomes y double prime plus y equal to 0. And as you well known, this equation has sines and cosines as a solution. So indeed, for very large x, the solutions of the Bessel equation of order 0, they do look like sines and cosines. As a matter of fact, I'm going to give you here the asymptotic behavior of J0 and Y0 as x goes to infinity. And these are expressions very commonly used in practice. So if you want to approximate this rather complicated series with cosines and sines as x goes to infinity, these are the two nice expressions that you can use. All right, again, you can. What I'm doing here is on this plot. You have the actual, for example, function J0 of x, and then you have the asymptotic approximations x goes to infinity of J0 of x, and you can see for quite small values of x, even for x equal to 1 or for x higher than 1, these asymptotic approximations are very good approximations of the Bessel functions. Okay, so now we move on to the Bessel function of order 1/2 to see if anything interesting happens with this equation. So this is our differential equation. So we're going to approximate again solutions in this series form. Again, take first and second derivatives exactly as before. The only thing that is different here is that this last term here involves this 1/4 coming from the differential equation. But apart from that, everything looks the same. So if you do the same tricks that I worked on the previous case, you can isolate the terms that involve x to the power r, x to the power r plus n, and then all the other terms x r plus n from n to infinity. So you get something like that. So your initial equation immediately you can see is r squared minus 1/4 equal to 0. So we have roots of r to be plus minus 1/2. In some sense, that's not good news because r1 minus r2 is equal to 1, which is an integer. So we know that something special may be happening for the second fundamental solution y2. So we need to investigate that. And of course, you see the recurrence relation relating here a1 and an minus 2 given by this nice equation on the bottom of the slide. So let me do the following thing. I'm going to start with the root first of r1 equal to 1/2. So for r1 equal to 1/2, you can see that this term is 0. So a0 is arbitrary, so you can actually take a0, if you like, equal to 1. And if you put r equal to 1/2, this bracket here is non-zero, so a1 has to be equal to 0. Now, if a1 equal to 0 from the recursive equation on the previous slide, then all the odd coefficients have to be equal to 0, and we have to concentrate only on the even coefficients that look like this. So basically, the recursive equation comes by taking this bracket equal to 0, and I simply have substituted r to be equal to 1/2. So we can compute the coefficients a2, a4, etc. This is the general expression on the bottom of the slide for a to m. And when you put all of this together, remember the solution is x to the power r, x to the power r. R is equal to 1/2, and the leading coefficient here, I took it x0 to be equal to 1. And you can actually rewrite this. Let's see if the leading term, if you take m equal to 0, you get x, and x minus 1/2, you get x to 1/2. And the reason I'm rewriting this bracket like this is because this series inside the bracket is nothing else but the Taylor series expansion around x equal to 0 of sine of x. So surprise, surprise, for the Bessel function of the first kind for order 1/2 is 1 over square root of x times sine of x. And the Bessel functions that is used in practice, it is normalized with this factor that you see here, square root of 2 over pi. So it has this form given on the bottom of the slide. So the singularity is 1 over square root of x, right? So 1 over square root of x times sine of x, and we have this normalizing factor of square root of 2 over pi. So that's the Bessel function of the first kind of order 1/2, okay? And So now we have to look at the second solution, and I remind you that the second solution, the first solution minus the second is an integer, right? 1/2 minus the minus 1/2 is 1. So strange things may be happening, but in this particular case, I'm going to show you that we are a little bit lucky, because if we take R2 equal minus 1/2, and we look at this, the second bracket here for R2 equal minus 1/2, this becomes 1/4 minus 1/4. So it's 0, which means A1 is arbitrary. All right. So in this particular case, not only A0 is, we can, is in principle arbitrary, but A1 is arbitrary. So we're going to have both even and odd coefficients for our series expansions that we're going to have to evaluate. And but somehow, because this term is eliminated, we have managed to actually get a series expansion for this case, R2 equal minus 1/2, without having to deal with the complexities of two equal roots. So for the even coefficients, if you plug in, if you take this recursive equation equal to 0 and you plug in R equal minus 1/2, the even equations can be computed, all of them, from this recursion. And I'm giving you some of these coefficients and the general expression at the bottom of the slide. And I can do the same thing for the odd coefficients. All right. So again, I plug in R2 equal minus 1/2. So for the odd coefficients, this is the expression. And when you put all of this together, the leading term again is x to the minus 1/2. And it comes out that the solution to this equation can actually be written as a combination of this bracket as a combination of sines and cosines, right? So this is the Taylor series expansion for the cosine. That's the Taylor series expansion for the sine. And that's your second solution. So we actually have managed to get the solution without doing anything fancy, the way we have seen for the case of two equal roots in earlier lectures. Now, usually we take as the second solution to be the term that involves only the cosine. And again, with similar normalizing term as what we have seen before. And this is a solution of the second kind of half order of the Bessel equation. And the general solution for the order 1/2 of the Bessel equation is what you see on this slide. Okay, so now if I plot these solutions, again, this is the J1/2, and this is the J minus 1/2. And again, they look, the leading singularity is 1 over square root of x, cosine and sine of x. And I remind you the asymptotic expressions, the approximations we had for the J0 and Y0 solutions for the Bessel equation of order 0. They were also having similar form, but with cosine of x minus pi 4 and sine of x minus pi 4. So the two solutions, they look very much related, with only difference having a phase shift of pi over 4. And you can actually look at the two graphs and convince yourself that this phase shift is pi over 4. All right, so let me just finish the lecture by taking now the Bessel equation of order 1. Exactly the same ideas, Taylor series expansion, x to the r times summation of an xn, and take the derivatives, plug them in the differential equation, and what we're going to do is we're again going to isolate terms that involve x to the r and x to the r plus 1. So that way we can have a general recursive formula. We can have the indicial equation being r plus minus 1. And again, you notice that in this case, we have two solutions that they differ by an integer, which means we may have to do special things to calculate the solution y2. So the recurrence equation again is given by putting this bracket equal to 0, and it is what you see on the slide on the bottom. Again, I am writing this as a general function of r rather than putting r equal to 1, because to calculate the solution y2, we may have to differentiate this equation with respect to r. So let me take first the case of the first root r1 equal to 1. So obviously this term is equal to 0. So when you plug in r1 equal to 1, you're going to get 2 minus 1, which is non-zero. So a1 has to be equal to 0. And if a1 equal to 0 from the recursive equation from this bracket being equal to 0, all the odd terms have to be equal to 0. And you are left with the even terms. And you can compute those exactly. And you see the general expression for a to 2m for m equal 1, 2 on the bottom. So when you put all of this together, you're actually getting our first Bessel function of the first kind of order 1 that looks like this rather complex series. If you take a0 to be equal to 1/2, you can simplify this as what you see here. And this function, obviously, you notice there is no singularity because r is equal to 1. The leading term here is x. So this thing converges for all x's. So it's an analytic function and is known as the Bessel function of the first kind of order 1. So we need now to compute the second solution, and then we're done. And in the second solution, unfortunately, we cannot go back in the equations we got from the differential equation, trying to see if an obvious power series expansion can be valid. So that will not work in this particular case. So we really have to look for general solutions that look what you see on the slide. And I remind you, in Theorem 2, in the previous lecture, we discussed this. So we're going to have to compute these coefficients A and Cn. And one way to compute this is to plug in this whole expansion inside the differential equation and compute from there A and Cn. And the other way, of course, is to compute A and Cn by using the expressions for An and computing certain derivatives as discussed again in the Theorem 2. So I'm going to avoid all the algebra and tell you directly what the solution y2 is. So here is the solution y2. And you remember we had defined in an earlier slide what these coefficients HM are all about. And so in this, so in this particular case, the J1 goes to 0 as x goes to 0, and it's analytic as we have seen before. But you notice that y2 is unbounded at x equal to 0. First, we have this log in here, and then, of course, there is the 1 over x term in here. So y2 is unbounded. So if I can give you a plot of the solutions J1 and y1, and by the way, similar to what we did before, this Bessel function of this second kind of order 1 is defined by linear combinations of y2 and j1. So rather than taking directly this Bessel function to be y2, we combine it with j1. And again, gamma is the Euler constant that we have seen before. So j1 is a bounded function that's analytic. It converges everywhere. And y1 is unbounded at x equal to 0. And apart from that, you can see that the nature of these Bessel functions for the Bessel equation of order 1 are similar in nature with what we discussed before. And the general solution, again, is a combination of the j1 and y1. So the Bessel equations are extremely important in practice because many problems they lead directly to approximations that take the form of the Bessel equation, and so there are equations that they come often. So you need to know what is the differential equation that we refer to as the Bessel equation, and also you need to know these different approximations of the Bessel functions, like the cosine and sine approximations that we have seen as x goes to infinity. All right, so that's the end of this short lecture on Bessel functions. We will continue more with the solution of differential equations on our next lecture. Bye for now.